Good afternoon, everybody. Thank you for coming. This is the Data Science Machine Learning Forum. I am Michael Walker with the Data Science Association, and we have a fantastic afternoon. I think it's going to be worth your while. We are so blessed to live in Denver, Colorado, with this beautiful sunny weather. I almost feel guilty about having you guys sit indoors when it's so beautiful outside. Machine learning is one of the hottest areas in data science, indeed in all of technology right now. And I think after today, you're going to see why. I just had a client talk to me, and he asked me, well, why all the excitement about machine learning? We've been doing machine learning for 40 years. This is an older guy. And I said, yes, but the difference is we have a lot more high quality data now. We have cheaper and faster compute. We have innovative data storage. We have better, more sophisticated analytical tools. So all of that is starting to come together so that we can do a lot more things. I think that we're at the very beginning of the high value that machine learning can provide, not only in business, government, but also in our personal lives, healthcare, fitness, just our quality of life, how we organize our lives. And I think that the tools, the technology that we have today are actually quite crude, but they're going to get better and better. And when they get better, we're going to be able to use the machine learning techniques that we have now that will innovate and evolve to do amazing things. So today, we have a number of wonderful speakers. We have from Teradata Aster a demo of some of the ski data that we have been playing with. If you stop by outdoors, we'll have a table there with a booth, and you'll be able to see a demo of how they do it. We also have my friend Hal Woods from HGST, who is going to talk about innovation in data storage. And it's really amazing the things that HGST is doing in data storage. And it turns out that's actually a more important part of machine learning than you may think. We have Jim Bates from Matt Barr, who's going to talk about machine learning and time-based databases. We have Andrew Weekly from NREL, who is going to talk about acquiring weather data. We have Charles Clifford, who is going to talk about machine learning use cases and Google BigQuery. We have Pete Cole, who's going to talk about machine learning in finance and trading, and that's actually a really hot area right now. The top hedge funds and investment banks are starting to ramp up their big data and specifically their machine learning departments, and they're doing incredible things. We also have Chris McClure, who is going to be talking about machine learning use cases with Microsoft Azure. And we have Chris Howard, who is going to talk about portable algorithms on a platform of portable algorithms. So without further ado, I'd like to, well, before I introduce, I'd like to let you know we have pizza. Feel free to help yourself. I would also like to get everybody to enter their information. We have somebody who's coming probably shortly. He's running a little bit late, Isaac. And when you go out or you see Isaac, if you would just give him your name, your email address, and phone number so that we know who is here. And I'd like to introduce the people from Teradata Aster. Thank you.
All right, it's hard to even think about talking about ski data, right? When 57 degrees, November. So bear with us. I know it's going to snow. It is the Rockies, so you guys will be able to go skiing. So I'm Mark Peterson. This is Elain Crutchley, and we started here. We wanted to look at the ski data, see what we had, and also use the Aster Discovery platform to see how we could answer some ski data questions. So we found it exciting. Hopefully you guys do too. Can everyone hear me all right? First of all, everyone in the back? I'll try to talk loud. I'm a bigger guy, so yeah. I'll come over here too, and not be in the way, because I am tall enough. I can. Okay. Can we dim? Can we dim the lights, somebody?
I don't know.
Okay. Where's the lights?
Good question.
To dim. If we can dim the. We can dim the lights here.
Oh, good.
Is that better? Yeah, that's perfect. Yeah.
No.
Right there?
Perfect.
Is that better for everybody? Good. That's good. Okay. So we wanted to use the Aster Discovery platform because Aster has a lot of benefits to answer the question. I mean, what's the best route? How to get to the ski resorts? We all have been there, right? You go in there, you get close to the Eisenhower Tunnel, and what happens? Traffic, and you can't get to the ski resorts. You sit in your car for several hours, and you just ruin your ski day. So we want to try to answer that question, how to make it so it's more enjoyable, and so you don't have to sit in traffic. But first, to understand that, I wanted to go through why do you need a discovery platform? Why use a discovery platform for your data such as Aster? And so I was reading a child's novel, a little old book with my kids, and we were reading The Blind Man and the Elephant. So I'm sure all of you have heard that book or are familiar with it. But these blind men, they thirsted for knowledge, right? They wanted to be able to learn about everything. And they heard the prince received an elephant. So the blind man went, they wanted to find out what an elephant was for themselves. So the first blind man, he touched the leg of the elephant, and he described the elephant like a tree, like an elephant's like a tree, because those legs are big like a trunk. Another one touched the tusk of the elephant. He said, elephant has spears, because he had the big tusks. Another of the blind men grabbed the hold of the trunk and said, an elephant is like a snake. And so all the blind men went through, feeling different parts of the elephant, and then they were sitting down in the shade, saying what an elephant was like. And then one elephant is like a tree. No, it's not. An elephant is like a snake. And they were arguing back and forth. And then this prince, he heard the argument. So he came out and said, hey, all of you guys are right, but all of you guys are wrong at the same time. And so he said, an elephant looks like a snake, it looks like a tree, it's a wall, it has spears. All these things make the elephant. So that's where you guys are wrong. And so that's where a data discovery platform like Aster comes into play. Aster lets you bring in data from your data warehouse, data from Hadoop, data from outside source, maybe weather data. Someone's going to talk about bringing weather data that you might not store in your data warehouse or in Hadoop. And it lets you bring in all of these different data sets and find the truth, right? So you can analyze them all. So you can see the whole picture of the elephant. You're not just looking at the trunk and thinking it's a snake. You're able to see the whole picture of the elephant. So that made sense for me. Hopefully it understands why you want to use a discovery platform. And what Aster does is it runs on Hadoop, it runs on appliance, it runs on commodity hardware, and it's SQL based, so the language of business analysts, and it has a lot of SQL MR functions, MapReduce functions, so you can do things quickly and at scale. And it also has the MPP, so the multi-parallel processing, so it processes data across all the nodes, so it's able to gather results quickly. Okay, so you can go. So this is kind of what it is. You just load the data quickly. Instead of an ETL, which everyone talks about, with Aster it's an ELT. You extract the data you want, you load it into Aster, and then you transform it there. It's very powerful from that. You ask questions of the data. What do you want to ask the data? What do you want to go? Then you run some SQL-MR functions and start making hypotheses. And then you get through, and you might ask more questions. Okay, so the skiing. Why are more people traveling on holidays than not holidays? And then you either operationalize your findings or you move on. So with Aster, it's an iterative process. You're always loading data, asking questions, and going quickly. A phrase that is used a lot, you want to fail quickly in your data analytics and your data science. Fail quickly, move on to the next thing, so you can keep going and find answers. Okay, so with the ski data here, we gather data from 5 different sources. We use data from the Colorado Department of Transportation with a highway road count, so it counted traffic at different locations. We use ski data, so snowpack and snowfall at different ski resorts. We wanted to look at how school days affect traffic, so we looked at data from the Denver public school system, temperature, and for just a fun little part to show Aster's strength with unstructured data, we looked at TripAdvisor comments for Colorado ski resorts. So we looked at TripAdvisor comments from these ski resorts right here that we did. And so we were able to find about 5,300 comments on TripAdvisor. And so some of the findings were interesting. But just to show you how quickly it is, so once you get your data set loaded into Aster TripAdvisor comments, with just a few lines of code, you can start extracting sentiment from all of those comments. So here's a SQL-MR function. So it's you select from this extract sentiment, that function, set SQL-MR, on your table, and the text column you want to look at, so that was the review. You're using the dictionary, and you're looking at the sentence level, and you're going to accumulate it by the ID and the review. And so with just a few lines of code, you can start gathering sentiment about the resorts. And so we looked at the resorts, and here's what they were saying. These are the words that people were saying about Colorado ski resorts. So it's interesting. I mean, a lot of what we all know. It's great. It's excellent. The resorts are top notch. It's fun. The Alpine slide showed up. So I know that there's an Alpine slide at Steamboat Springs. Is there any more Alpine slides around that people are using? But it's interesting that there's more than just winter activities people are using resorts. That people are commenting about summer activities as well. So then we wanted to look at the sentiment. So we looked at the sentiment of all the resorts. Winter Park had the lowest, just a score of 4, which is really good, out of 5 comments. So there wasn't a resort that had bad comments. And Aspen Mountain had the highest at 4.9 out of a scale of 5. So we dug in a little bit deeper into Aspen Mountain. What are people saying about Aspen Mountain? And here are the words that we came out with, the sentiment words that people are saying. It's great, friendly, great staff. So you can imagine, Aspen Mountain has great staff. They're really catering to that clientele. It's beautiful over there. And that's what people are saying on TripAdvisor. And then we looked at the negative sentiment of Aspen Mountain. And it wasn't easy. I mean, we had to dig in a little deeper because, like we said, people aren't saying anything bad about the resorts. But these were the words that did come through. People were cold. It was challenging. So maybe Aspen Mountain can say, hey, this is more an intermediate resort. But the things that I found interesting is pricey and expensive. But we all know Aspen caters to that clientele, right? They're catering to a more higher-end clientele. So if you go to Aspen and you aren't aware that you're going to spend more money, of course it's going to be expensive and pricey. You might have sticker shock there. So then we just dug into a little data we wanted to look at. So we looked at IA-70 at Eisenhower Tunnel and traffic counts. This is average daily traffic counts. Whether it be in the morning, and the evening. And so this doesn't say anything that we don't know, right? More people travel on the weekends, on the roads, less people travel on the weekdays. But we dug in a little bit further, and what was interesting was on this next couple slides, we pulled out, here's 5 routes that we had for traffic counts. And you can look at, out of all these 15 days, so this is over a 3-year period, there's 15 days here. 13 out of 15 come during ski season, in the mornings. So this is mornings. So morning people are going to the skiing, right? They're hitting the slopes in the morning. If we go to the next one and we look at the 3 busiest days by route location in the evenings, a different pattern emerges. More people are traveling in the summertime, in the evenings. So you might want to start planning your trips. Maybe you want to travel the night before to get up to the mountain, which is, it is interesting that people are, there's a different patterns there. But if you think about it, maybe it's because the weather's better in the summer. So you're not worried about the weather, so you're traveling in the evenings more. So that was an interesting piece that we found. Then we wanted to look at what's correlated with traffic. And so here we have traffic, and we can see the different variables that are correlated. So max temperature, there's a positive correlation there. Humidity, a little bit of a negative one. Visibility, a positive one, and wind speed, a negative correlation. So you can imagine when the temperature's warming up, it's clear, more people are on the roads. When it's not as clear, the wind's blowing 40 miles an hour. I'm from Wyoming, so I know what wind's blowing, but it blows hard and you get that wind blowing. You don't want to be out on the roads then, right? After you have a fresh snow and the wind's blowing, that doesn't make it fun. So the data shows that people aren't traveling as much. So the next thing we did is we wanted to use the GLM function just to see if we could predict traffic counts. And so we used 7 variables to predict morning traffic at the different locations. And this is another, so just with 8 lines of code with a SQL-MR, you could do a GLM model across billions of rows and gather results within just a few minutes, which is really incredible that you can do that. So you can do this at scale. So the variables we used to predict traffic was highway location. So we had 7 different locations scattered throughout that the CDOT provided. And so highway location depended. Of course, there's going to be more traffic in the Denver area than there is going to be up on Highway 9. There's going to be a lot less traffic. So the model accounted for those differences. Days of the week, there was a positive or a negative correlation. And then, can you go back just a little quick? And then direction. Depending on the direction with the day of the week, it's either will help, or there'll be more people driving or less people driving. Snowpack had increased traffic. So when the snowpack's getting, more people are hitting the road for the slopes. As temperature and humidity. School days, and this is probably one we could all realize, but school days, when there's less people, when there's nobody in school, the days that people don't have school, whether it's a holiday like President's Day or Martin Luther King Day or spring break, there's more people on the roads those days too. And so our model that we created here, the GLM model, it accounted for 90% of the variation in traffic with those few variables. So you can see the output here.
Okay, and then what I kind of focused on, we had 10 different checkpoints in our traffic data. So it was just an aggregate of everyone who drove through that area. So this is just an example of one of the checkpoints. It's at Henderson Road up to Winter Park. And this is just the time series output of the traffic data over 3 years, I think. So the first thing you're going to notice is there are these peaks, right? So to kind of predict our traffic, we want to kind of determine where the peaks are. So these are 2 example days, July 28, 2012 and February 16th. So we do want to account for that, and ARIMA is kind of a new function for Aster. We have all these machine learning functions, but we just got this kind of forecasting model, so I want to try it out. So there are about 200 days between the peaks. I just estimated a little. Different checkpoints were really different. Some of them were 7 days, some of them were monthly, some of them were 135. It just really depended. And both of these dates are Saturday. So then this is the output of the ARIMA model. It's an exponential smoothing model. And you can see you do have these peaks at 50 and 250. And here's just an example of the code I used to produce this. As you can see, it's really very short, very simple. I just had to, do the input table, signify which columns are the dates, which columns are the values, which in this case is traffic, and then just name the output tables, and do the orders. And I tried several different ones, and most of them, an exponential smoothing model fit pretty well. So then I wanted a way to visualize all the checkpoints at once. So I decided a map might be the best idea. In a very kind of unscientific way, I wanted to color them. I wanted to see, okay, what checkpoints are having above average traffic or below average traffic. So I just kind of subtracted the daily traffic prediction from the checkpoint average traffic. So the deeper red are more traffic. And this is also on a Saturday, this February 14th. So you can see that the point over near Denver, it's having less than average traffic because it is a Saturday. And this is the point we were looking at before, and this is right on the top of the peak. So you can see it is having more traffic, people going up to Winter Park on this Saturday. Okay, so the next thing I want to look at is how many people are taking each route and which route is the best in different weather conditions. And this is just an output from Google Maps. I'm sure everyone recognizes it. But there are some things Google Maps cannot answer. So I moved recently across the country, and I was in my tiny car. I could not see anything behind me, and I really just wanted to take a route where no other cars were on the road. So I figured that might be the same with people who have all their ski gear. So you can't see behind you. Might be snow conditions, like I want to take the route with the fewest cars. So I made this app in App Center, which is an Aster kind of overlay. And you can input your starting location, which I looked at Durango in this case, and the resort. And this slider is the weather condition. So on the very far left, it is mild weather. So then the output of this, I wanted to have the breakdown of how long it took on each route. So obviously, the shortest one is 160 to 285. So this corresponds over here. So the thickness of the line means more people are taking it in this Sankey graph. So, so I was like, okay, like there are a lot of people taking this route. What if I want to add an hour? So look at this 550 to 50 to 170. And okay, there are like much fewer people taking this, so maybe this would be a better route for me if I was okay with adding an hour, but seeing much fewer cars. And then here's just the code I used for this visualization. Very easy. This is our npath function. One of our most popular functions, just gives like a really quick visual impact. Very popular, very easy to use. So those are the things we did. Just to, I made up this last data. We did not have the data on the car level, so I just threw some data together just to demonstrate what could we do with Aster if we did have this data. So we could do that optimal path, but we could also, with the data we had with that aggregate traffic data, we did predict traffic looking at factors in GLM. We had the advantages and disadvantages of each resort with our text analysis functions, and it can be done in real time. So here are just some resources. Aster Express, the amount of data we used, it wasn't a ton of data, so it could easily be loaded in Aster Express. And there's really good resources on the user community to download it and get started with your functions. And if anyone wants to see like demos of any apps I did or any other apps that are kind of commonly available, we'll be sitting outside, so you can come see us, talk to us. Oh, does anyone have any questions?
So Aster is the NoSQL horizontally scalable product in contrast to Teradata's traditional product, which is more RDBMS. Is that correct?
Aster's a relational database, but it also has an Aster file system, so it's kind of in a way like a Hadoop, but most people use it as a relational. So it's based on PostgreSQL.
Because you kept mentioning SQL MR, so.
Yeah, they're functions that are written in Java that the Astra engineering team's done, and they put them in a SQL. So it has a Java wrapper, and so it's doing the MapReduce function for them. But they wrote it in SQL because that's the language that business analysts are comfortable with. So Astra's a product that they want to take it so the business analysts that are used to SQL, use SQL, can have machine learning and do those things. Does that make sense?
Yeah. So one final question. So I saw a TF-IDF table. Is there an Astra function to generate that table?
Yes.
Okay.
Yeah. So that's one of the Astra functions. There's 140 more or less SQL MR function, but then you can write your own in Java. There's an Astra Eclipse, Astra Express Eclipse, where you can write your own SQL MR functions in Java, and there's tutorials on that too that you can learn. And another thing too with Astra, some of you guys might be more on the R side. Astra now can run Astra R, and so you can run R at scale instead of having limitations of doing R in memory. So that's another thing that's on this screen. Yes, sir?
When you're importing data, large sets of data, does Astra support different styles, different types, different data types? So if you got something coming in as .data or .r for dark, who knows? You know what I mean? Will it understand that, or do you have to put it in the right data type first?
We do have different connectors. So if you have XML data or JSON data, we have connectors for that. If it's in like a more unstructured type, it is pretty easy to write your own connector to implement.
I have a question about the Astra R. So is that like built upon CRAN packages, or is there some in-house code for that? And how does that compare to Revolution R?
So she wants to know, did everyone hear the question? She wants to know if Astra R is available in CRAN, right?
And then it's built upon packages from CRAN.
Oh, if it's built upon packages from CRAN, and then how it compares from Revolution R, right? First of all, the Astra R it has nothing to do with CRAN. We didn't put it through CRAN because it's proprietary software. So that is only available to our clients, the Astra R package. There is a toaster package that was built upon CRAN and is available in CRAN. So that's just a lightweight package you can connect to Astra, and with that package. I have never used Revolution R myself, so have you? So I imagine it's a lot of similarities from what I've read about just when they do the competitive landscape, and so they're very similar in that sense. That is comparable. But I've never used Revolution R, so I don't want to misspeak. So I can get you further information after if you give me your contact or something, and I can research and answer that question better for you. You, right?
Is the SQL MR, does it have analytic functions as well?
Oh, yeah.
It's pretty straightforward.
Yeah, it has pretty much every analytic function I used in grad school. Like it has like naive Bayes and I'm kind of blanking.
Random forest, GLN, naive Bayes, bunch of text functions. There's over 140 of them.
Like association
correlation,
analysis,
yeah, like your market basket analysis, we call C filter, path and pattern analytics is there, and so it's just 6, 7, 8 lines of code, and you run it on.
One more question. You were talking about the App Center. Is that so that you can build apps to actually integrate with Java applications that you have running and pull some of your data into that? Is that what that's about?
So App Center is kind of an overlay on top of Astra. So I coded the apps, but if I wanted to give it to like maybe a business user to play around with, like say if we had like a model and we want to experiment with different variables. I could give it to a business user, could put the variables in. It's just a point and click overlay, and they can get output out, like I got output out.
Is it straightforward to integrate it into applications you already have?
Yes.
Yeah.
Oh yeah, it's really easy to use. I was really scared of it for a while. It looked complicated, but it's really just a wrapper. If you've used like our Shiny or VBA, it's very similar.
And you can create, like you said, Java apps through App Center to import data or something like that, that if you wanted to. Yeah. In the back.
So you created a word cloud for sentiment analysis. How would you find out what the context was? Say the word challenging appeared right behind the data set, so that was right on top of the word cloud. It could have been, it was very challenging or it was less challenging. How were you able to capture the sentiment?
Right, so you want to know how it distinguishes very challenging to less challenging, right?
Yeah, the context.
Yeah, the context. And so that's the basic function of it there. And so I can't tell you how accurate the out of the box the extract sentiment function is. So I really couldn't tell you if it's 90% accurate or whatever. I'm not familiar with that. Are you on the extract sentiment? How
I do
out of the
not,
box?
but if you did want to get some more context, we do have a function called ngram, and it looks for words within a certain distance of each other. So if I did see challenging, and I was like, okay, I don't know what this word in front of it or after, I could look in the first 2 words or 2 words after and see, okay, is it less or is it very, things like that. So it just takes some additional analytics.
Yeah, how does Aspen compare to using like Monetizing and ZR? Like a lot of my transforms that I do, like I just push them into Monetiza bots. Does Aspen like at what speed or how does it work?
I've never used either of those products. Aster is fast, and it is, as it's tested, it is very fast. But I don't want to misspeak and give you numbers that I don't. But if you do give us sort of your information, we can sure gather that information for you. I don't think either of us want to misspeak and give you.
We do have a benchmark team, so we can forward your information along to them.
Yeah, we can get that answered for you. We just better not misspeak. Was there any, you had a question here, right?
Well, yeah, he asked. It's about the speed.
Okay.
Yeah, thank you very much, Mark and Elaine. Our next speaker is Hal Woods. Hal is a good friend, and I can tell you he does amazing work innovating in data storage with HGST, and it's actually turns out to be a really important part of machine learning requirements. And I'll let Hal tell you about the latest innovations in data storage, but I also want to let you know that Hal and HGST has been kind enough to offer a 1 terabyte hard drive to give away as a prize. So what we're going to do is Isaac is going to hand out sheets of paper. If you would put your name on the sheet of paper, and we will hold a drawing later, and the lucky person will win a fantastic hard drive. Also, Isaac is the man who is going to be taking down our information, so I would respectfully ask that everybody at some point, especially if you're leaving, stop by with Isaac and just give him your name, your phone number, and email address so we have a record of everybody that's here. Thank you, Hal.
And then I'm gonna pass these out, and then I'll collect them after Hal speaks.
Yeah, just push escape.
That way I don't force you guys to not pay attention or rush or anything.
Oh, great. So, Michael mentioned I'm Hal Woods. I'm the Vice President of Technology and Advanced Development for the Cloud Infrastructure Business Unit at HGST. Folks may not know who HGST is. We were the inventor of the original disk drive, but we were known by a different name at that point. Anybody want to guess? IBM? So, been doing this for a little while. I'm going to talk about a few things. We've got a short amount of time. I'd like to talk about a lot of things, but we'll pick on a few key points here. Before we get started, I've got some bad news for you folks and some great news for me. That is, you guys are all hoarders, addicts, as a matter of fact. You want to keep everything. when I went to do this presentation today, I always come to these things with a memory stick, just in case of some glitch. And I went through about 10 memory sticks in the drawer before I found one, and I kept looking, and it's like, those are all full. And I dare not delete anything, right? Just because I just don't know what I'd be deleting. The key thing is, you don't even think it's likely to be useful, but you keep it anyway. And you'd store even more if you could. So what this chart is showing is that today we're throwing away useful data. Somebody's very excited about that. We get rid of more data than we actually keep, even though we think that data is going to be useful. And so that's kind of an interesting trend for the folks in this room, because really what you want to do is keep everything. You want to have the opportunity to keep it, because right now, when it's generated, you don't know if it's going to be useful, right? But there's a chance later that it will be. And so, you keep it, maybe useful, probably not. But today, state-of-the-art technology is I can store about 400 gigabytes in a cubic inch. So we're trying to help. When you want it, you want to get it very quickly. So the state-of-the-art from a solid-state technology perspective is about 150,000 transactions per second per cubic inch. But the challenge is, how do you find the important pieces? So how many folks here think, how much does it take to store a gigabyte of useful data? How many people think half a gigabyte? 5 gigabytes? 100 gigabytes? It's all those, right? We have technology to compress or deduplicate data, so we can take most data and compress it by about a factor of 2. But if you look at most of the social media sites, what you find is they typically keep 5 to 10 copies of a given piece of data, right? Because they need to make sure that should something go wrong, that data can be made available. And if I go to classical enterprise IT, they take that data and about once a month or once a week or something, they make a full backup, right? If you take that over a couple of years period, right, you end up with a lot more data than you started out with. So it's just an interesting challenge as we look at trying to store all the useful data. How can I afford to do that, right? So I'm here to tell you, store it all, store it forever. And folks in the data storage industry, thank you for being addicts. Right? It's an interesting challenge we all face today. So storage may not be the most exciting topic out there. So I'll try to say, why are we talking about data storage? I'll talk a little bit about, some of the technologies that are becoming more interesting around storing your data, some changes that are going on in the industry around protecting your data, especially at scale. One of the big challenges, obviously, is how do we monetize that data? What it really comes down to, if you're running a business, is I want to extract value from that information. And then there's one technology I want to touch on, and it's related to some recent announcements by some key industry players around storage as memory, and I'll talk a bit about why that's going to be important. So why talk about storage? We're facing a fundamental transformation in every aspect of our lives associated with what some of the analysts call a third platform. And this is the move to cloud, big data, mobility, social media. All of those things are generating massive amounts of data. That's what the folks in this room live day to day. And to try to find an interesting illustration of this for some of the folks within our company, I did a little research and found an IoT application about a Dutch company that's trying to put sensors on cows, right? You might ask, why would you do sensors on cows? There's actually a big problem in the industry of cattle with theft, animals getting sick and them not knowing it, that sort of thing. And so they really want to put IoT sensors on cows. If you do that, every cow generates about 200 megabytes per year. So that's interesting. So what does that mean? Well, there's 1.5 billion cows in the world, 200 megabytes per cow. That's 300 petabytes per year. As I said, I love my job, right? That equals 100 racks of storage at the state-of-the-art technology today, or roughly 10,000 cow years per rack. I was at the Amazon Web Services Invent Conference a couple of weeks ago. Anybody else get to go to that? Neat thing. They did not offer cow as a service. Most everything else is a service, but they're currently not offering cow as a service. So what's some of the things going on in storage that could help you do your job? So we mentioned earlier that people can't afford to store all their data. And so HGST, this is an example of an HGST product. This is really an industry trend. So when I talk about HGST specifically, really this is what's going on in the industry. Right now, we're at about almost 5 petabytes per rack. Okay, that rack can generate about 3.5 gigabytes per second, and it's a scale-out architecture. So we have customers who will deploy 10 or 20 of these racks as a single system. 15 nines of durability. Amazon uses a term called durability to talk about how likely it is to lose a single object. 15 nines means about if you have 1 billion objects, you'll lose 1 object every 1 billion years. So pretty unlikely. They're very efficient. So one of the things that I mentioned earlier is how much does it take to store a gigabyte? In this case, to store and protect that gigabyte from all the way up to site level failures, right? It only takes about 1.5 gigabytes to store a gigabyte of data. And so we can store it very efficiently. And it costs about $100 per terabyte. Now, just a few years ago, I was 16 years at Hewlett Packard in the CTO office for the storage business. And we sold storage at that time for about $1,000 a terabyte. So just the amount that it's coming down is really trying to enable you to store all of your useful data. We tend to talk about storage in 2 buckets, big and fast. So what is the state of the art in terms of fast storage? So today you can buy a half-height, half-length PCIe card, right? Getting down to the weeds of the hardware, that stores 3.2 terabytes of data and can do 750,000 IOPS per second. Why is that interesting, right? The ability to do analytics and machine learning is really about 2 things. How much data do I have to operate on, and how quickly can I access it? And if I can do things very quickly, I can make faster decisions. If I can store lots of data, I can make better decisions. One of the interesting challenges in the industry right now is you see the latency numbers, 20 to 2,000 microseconds. Why is that important? Most scale-out applications that you see in the big social media sites and everything are dominated by what they call long-tail latency. The slowest transaction dictates the overall service time of the transactions. And you see 2 orders of magnitude difference there. And so there's a lot of work going on in the industry, and I'll show that in a second, to take that and compress that down to be more predictable. Used to be solid-state drives, right? When you use a solid-state drive, everybody worried about it wearing out. Right now, we've essentially addressed that problem through very careful management of the underlying flash media, and can get about 2 million hours MTBF, which is roughly the same as a standard conventional disk drive. So you see $100 per terabyte here, $1,000 per terabyte for the solid-state devices. Performance costs something. So where is this going? So on the big side, we're getting about 10 petabytes per second, or 10 petabytes per rack in 2018, and about 10 gigabytes per second. And we're blending the performance and the capacity side by doing things like tiering, where a working set can be pulled from inexpensive media into fast media for you to operate on, and that can significantly improve the transaction time. One of the things I had up here that I brushed by was this notion of co-located compute. Why is that important? Well, essentially, if I've got tens of petabytes of information and I need to push that across the network to the compute, right? That time, that network time is going to be the dominating factor in my ability to do a transaction. So we're starting to take these storage systems and put the compute inside them. We can put high-speed networking inside that rack and co-locate the compute and do things much more quickly. The chart over on the right is trying to address this notion of latency. What they're doing is through very careful tuning and optimization of the protocol, standard interconnects, we're able to go from 20 to 2,000 microseconds down to something like 2 to 5 microseconds. So we've gotten a lot faster, and we've narrowed the range, the average transaction times. So those are significant improvements in overall application performance when it's using this underlying fast media. And then you see down at the bottom here is ENVM. I've got the slide later that I'll talk more about that. So the next thing is protecting your data. And I just moved to Northern California from Colorado Springs. So when I come back here, it's really dry. So every once in a while, I got to stop and take a drink. So it used to be when we built storage systems, we worried about things like disk drives giving us errors, having multiple disk drives fail at once, or trying to recover from a natural disaster. Maybe I have a fire or something like that. But as systems have grown and we've gotten these many, many petabyte systems that may be geographically distributed, a whole new set of problems have come up. How many folks, you know, if you watch the news, right, you get outages at a Facebook or something like that. What you typically see is one of these two things: service and maintenance or upgrades is the cause of the outage. These systems have become so complex that it's very difficult to understand the side effects of making a change in one part of the system and other parts of the system. So we spend a lot of time in designing these large systems dealing with service and maintenance and upgrade concerns. Bugs are always there. Lost metadata is an interesting one. If we're the storage, the back end, the very bottom of the stack, if you will, oftentimes the data will have been encrypted 4 or 5 times by the time we get it, right? Any one of those layers that encrypts data, if I were to lose a key, I've got a complete data loss. And so things like lost metadata, the hash tables, if I'm doing deduplication, things like that become big concerns. And so there's an interesting conversation that needs to be had in these application stacks that are many layers, right, is be careful with all that metadata, because the loss of that metadata can be a complete loss of the overall data. And then there's unnatural disasters, right? More and more things with people with bad intentions trying to do things to your data. When I was at HP, there was this notion of a treadmill we put customers on, right? And this wasn't just HP, this was all of the enterprise providers, where, you know, they want to do a big services engagement to make sure that when we configure that system, it operates. If anything ever breaks, right, we want to make sure we're right there, right at the moment it breaks, to service that. And we want to make sure we sell you the upgrade packs so that you're constantly upgrading the system. If you think about what we talked about before on the previous slide, those are the things that can often cause problems. So as we think about systems today, right, we'll say, if it breaks, don't fix it, right? We're going to provision the system so that most of the common failures can be accommodated without ever having to replace anything. Or once a month, there's a guy who comes around with a little cart, right, and he replaces the components that are broken, but there's no urgency involved in that, because the system is designed and resilient to those sort of things. Partially broken may not really be really broken, right? One of the trends in hyperscale is to use off-the-shelf equipment. And so when we do that, we provision that so that when things break, right, we can just continue operating. Another thing that's always an interesting dialogue is the people who want to get the last 1%, right? They want to tune it to the nth degree, they want to get all of that. And while I understand that, oftentimes those unintended side effects, unintended consequences can come back to bite you. Don't let others break it. There's a lot of conversation, even within HGST. If you think about us building millions of disk drives annually, we store about 1,000 parameters off the manufacturing line for every drive we build. That goes into AWS, right? And we run analytics at AWS on that. Right now, I think we've got around 2 petabytes of data in AWS. And there's an interesting problem. Has anybody got a lot of data in AWS? And you try to pull it out? It's really expensive, really fast when you want to use it. And so there's always this debate, partly around security, but more and more around cost of, should I go to the public cloud, or should I implement a private cloud? And finally, a big property of most of these big object stores and big storage systems is they're immutable, right? So when you come in and store something, it can never be changed. If you need to change it, you create a new version. And that creates some interesting opportunities around data provenance, auditing, those sort of things to keep some of these things in check. Finally, there's monetizing the data. I think this is all familiar territory to the folks here, right? But it's these things in aggregate that are interesting. I was in London here a few weeks ago talking to a wireless service provider. And the wireless service provider is going to all the large retail shops and offering to put in essentially free Wi-Fi. And why would they do that? Well, what they're doing as they install that is they map out the store, right? And they can locate within 1 meter where the shopper is at by pinging off their wireless connection in the wireless router. They can triangulate that down to a 1 meter location. They then know the mapping of the store to know what that customer is looking at. And the dwell time of that customer may cause them to push an offer to that customer to buy. And so they have all this big data analytics, meaning batch analytics that they've done so that they know what's the demographic of that customer. If it's a wireless service provider, in this particular case, it's one of the dominant ones, they know that customer's address, so they know their demographics and average income, right? By tracking their progress through these retail stores, they can know what interests them. And their eventual intent is to basically say, if this customer dwells for a while, right, I'm actually going to run an online auction of pushing that offer. So if they're at Harrods and they're not buying, Bloomingdale's can push an offer, right? So it's this interesting blend of how do you monetize as this wireless service provider this information they have for their wireless provider or wireless customers. They now have a lot of information about them. Now as they go through their daily lives and do things like shopping, they can monetize that information very successfully. So last one is storage as memory. So what do I mean by that? So a way to think about it is, what if I could keep my entire working set of data, right, in memory, meaning at nanosecond sort of access times, and very close to the CPU, and it's resilient, it's available, it's persistent. All the rest of my data is stored in some place like one of these systems we talked about earlier and accessible in just a few milliseconds. This essentially is creating a new memory hierarchy where things like software-defined storage and solid-state technology are interesting. Low latency commodity interconnects are enablers. So this was an abstract conversation that up until a couple of months ago, when Intel announced what's called the 3D crosspoint memory. Anybody hear that? Mostly software folks in the room. Why is that interesting in this conversation? So essentially, with the Skylake processor release that Intel will make next year, you'll be able to have persistent memory on your memory bus. Initially, that will be on the order of a terabyte or so, but think about having tens of terabytes of memory that's persistent available right next to your CPU. What would you do differently, right? Right now, many applications are written, right? One, assuming the memory is not persistent, so they do journaling and logging and all this other stuff to protect in the event of a power failure. What if I didn't have to do that? The other thing is, I've got an order of magnitude increase in the amount of memory, right? That's going to make it so a much larger number of working sets are going to fit in memory versus paging it in and out of the system. I can fundamentally construct a different type of application to service transactions, perhaps an order of magnitude more quickly, given that the way I write applications today is trying to deal with both far memory or even storage, as well as the notion that memory is not persistent in the case of a power failure. So in about 2017, you're going to start seeing the beginning of this journey. Intel has been very active in a number of the standards consortiums around creating new processor instructions, creating new ways of synchronizing transactions. All of that is the beginning of this journey to have basically very, very large amounts of memory persistent memory associated with the compute. So this is going to fundamentally change the storage landscape as well. Today, we kind of have this tiered notion of, you have the memory subsystem and then the storage subsystem. Those lines are going to blur, and you're going to have memory storage in the backing store, which is these large storage systems, all be just this continuum of storage, and most of the data will reside in storage or memory that's accessed in a nanosecond sort of time frame. So take questions if folks have them about the data storage technologies. My mantra is, my goal is to make it cheap enough and fast enough to be able to store all of your useful data. That's the goal. What I know is you guys are going to generate more and more data. That goes without saying. You look at IoT, the move to 4K for video, all those sort of things just cause the ongoing explosion of data. I know that the business I'm in is going to be healthy for a very long time. But what I want to do is make it so that you don't have to ask this question, is this data, this piece of data that I'm working with right now, is it useful enough to store? I just want you to be able to store it, because that way you don't have to know that up front. That's the challenge of analytics and big data. So I just want to store it because it might be useful for something I haven't considered. So questions on what I've shown or any other storage technologies? Yep.
Are you, in terms of the hardware, software interface, and information security, which kind of slows things down a lot. Are you guys, do you interface with that in the hardware way at all?
So
I mean, is that on the dashboard or the radar for let's address this?
So it's an interest. So the question is about what do we essentially do with security?
Yeah, and not data security, but information security. Hackers getting in, whatever. I know there's a bunch of hashing happening.
So the general way the storage industry tries to deal with that is they punt and say we will deal with whatever the enterprise security is, we will conform to that. So we don't try to get too clever inside, other than we've become very, very sensitive to closing all the back doors. So I don't know if you know that there's another major drive vendor in the world, right, other than HGST and Western Digital. NSA had a demo of a hack where they were able to go in and access data on that device by basically manipulating the firmware externally. And so, big uproar in the industry, right? Make sure you close all those little doors. The reason those doors existed is that what I talked about earlier around potential loss of metadata and things like that causing massive data loss. 20 years ago, everybody left a back door in so that we could help recover data in the event of those sort of things, either multiple failures or loss of metadata. Now, all those things are being shut down and controlled very tightly. But in general, we deal with security by looking up into whatever the enterprise security approach is. We try to connect into that rather than solve it internal.
Is that a business risk for you guys, that like you make the fastest thing in the known universe, but once it hits that edge, it just stops? It doesn't matter how fast you make it, and the customer is just going to say, gosh, my data is slow.
So maybe I don't understand the question.
Well, there's a layer of security that gets applied to when you go to access a piece of information, and I don't know where a customer is going to point the finger of why is my thing happening so slow. I don't know that a lot of people think it's because of all the security that's happening.
So yeah,
piece of hardware.
Maybe a way for me to respond to that is it's not uncommon at all for us to get a call about what the customer perceives as a poorly performing system, right? And they point somewhere, right? We get the call, obviously they pointed at us, right? And it actually is very difficult at times to try to sort through. It's like we're not getting any requests for anything. It's not us, right? But oftentimes that takes expertise beyond our capability. Other than we can tell the customer, we know it's not us, but we don't necessarily know where it is. It's one of the challenges. Any big, large-scale system, when you have a performance issue, is what's the bottleneck. So, other questions or comments? Again, maybe not the most exciting topic around, but what I want to do is make it so that when you're storing your data, right, you don't have to say, I just can't afford to store this little bit, because there's value in storing that. Yep.
Yeah. How is that Intel in-memory storage different than something like SAP's HANA software? So
SAP HANA is an in-memory database, right? But it's written with the notion that the memory is volatile. So every transaction, as the transaction proceeds, they will be synchronizing that to a persistent store, usually an SSD or a disk drive. In the event the memory, if we have a power loss and the memory gets lost, right, they can recover from that. And if you think about the number of processor cycles or the number of instructions required to do all that synchronization, right, it's really slowing down the potential of the application. Yep.
I was wondering if you had any opinions or thoughts about the migration of things where, things that were going to software tier, like key value pair storage, being pushed down to the hardware tier, the storage layer. What do you think about that?
Well, so the big rack that I showed earlier is an S3 interface. It is a key value store and object store. It would be interesting to maybe follow up conversation. We have the ability to put a key value interface on the drive. Right? We're getting some of the non-relational database folks saying, I might be able to write my application a little differently if I had a key value interface instead of a conventional block interface. But they haven't been able to describe the benefit. And as you might imagine, a new interface on a drive is a big effort. So we're starting to hear about that. What we're trying to figure out, though, is what is the underlying value, right, that offers to the application, such that, again, the overall system performs better in some way. So I think we actually have prototypes of that sort of thing running. We're just trying to figure out whether we should productize it. Other questions? Yep.
Yeah. in case of inconsistent read and writes, are there any more instances of data created? Like if one instance fails, like 2 instances get created automatically and support user data?
So inconsistent reads and writes. So what do you mean by inconsistent reads and writes? You mean you read it once and you get a different value, and read it again you get another value?
Yeah.
So the storage industry goes to great lengths to try to avoid those sort of things. Even in our S3 object store, which are typically considered eventually consistent systems, right, where that might be possible, almost everybody who offers that type of storage in the industry has moved to a consistent model because applications just don't know what to do when imagine 2 members in a cluster read something for quorum or something like that and get 2 different values. We moved to a consistent model because the applications didn't tolerate an eventually consistent model.